The single server queuing system that we're going to start with has one server and a queue. Entities arrive externally, and if the server is idle, they immediately start processing. If the server is busy, they get in line. So a typical configuration that you see all over the place at ATM machines, at fast food restaurants, basically anywhere where you have entities that are competing for a resource for processing. And so what we want to look at is simulating by hand the queuing system. And so what we're going to do is define the system state and see how the system state can evolve over time. So when we think about the system state, we're primarily interested in two things here. We're interested in the number of entities in the queue, which I'm going to call NIQ, and we're interested in the number of servers busy, which I'm going to call NB. And so our number of entities in the queue, this can be 0, 1, 2, up to some arbitrary number n. And for our single capacity server, single unit capacity server, this is either going to be 0 or 1. And so we think about our system state overall. System state, it's a combination of these two things, number in queue and number of servers busy. So for example, if the system is what we would consider empty and idle, so the server's idle and there are no entities in queue, our system state would be 0, 0. And when a customer arrives, so the server's idle and a customer arrives, and so what happens, the server immediately becomes busy. So our system state would transition to state 0, 1, indicating that there's still no entities in the queue, but now our server is busy. And so this is going to happen when a customer arrives. Customer arrives. And let's say that another customer now arrives, and now we transition to state 1, 1 because the server's busy with the first arriving customer when the second customer arrives. So this also happens on a customer arrival. When a customer finishes service, so if the server's busy and there's one entity in the queue, what happens? Well, the entity being served departs. The entity in the queue then moves into service. And so we then transition to 0, 1 because now we have 0 in the queue and our server is still busy. And so this happens on a customer completion. So at this point, we can have the customer being served can finish, in which case we transition to state 0, 0. We can have another customer arrive, in which case we transition to state 0, 1, and so on. So for this very simple single server example, there are really only two things that interest us. There are two so-called events that are of interest to us. That's when a customer arrives, in which case one of two things can happen. Either A, the server's busy and so the queue gets longer, so the number in queue goes up because the server's busy, or the server is currently idle and when the customer arrives, the number busy goes up. The server becomes idle. The second event that we're interested in is a customer completion. So customer completion. And again, there are only two things that can possibly happen. One is there are no entities in the queue, so the number busy goes down, so the server that was busy then becomes idle. Or B, there are entities waiting, and so the entity being served leaves. The next entity in the queue initiates service. So in this case, NIQ goes down. And so again, when a customer arrives, we either increase the queue length or increase the number busy. When a customer departs, we either reduce the number busy, in other words, set the server to idle, or reduce the number in queue. And in our system, nothing else really matters. So the fact that a customers being processed, undergoing service. So the service process evolves, but we really don't care about that. So we only really care about when our system state can change. And that state can only change when a new customer arrives or when a current customer completes service and departs the system. And so this is a distinct characteristic of discrete event simulation, in that the system state changes at discrete points in time. So let's look at an example of building the event calendar and doing a simulation manually. And so we have a set of entities here, 1 through 10. It doesn't matter what they are. Let's assume these are students waiting in line for my office hours before a test or something like that. And so you can see that I have arrival time, so I'm just starting at 0, the time that my office hours start. And the first student arrives at time 0, and the second one at time 4, and the third one at time 10, and so on. So we're just evolving time, and we know what time the individual students are going to arrive. Similarly, when a student arrives, we have the time that it's going to take for me to help the student. So the first student arrives at time 0 and takes 5 time units for help. And so what we're going to do is we're just going to run the system using this sample data, and we're going to construct what we're going to call the event calendar, where we keep track of the time that individual events occur, and we're keeping track of our system state. So recall that our system state is comprised of the number in queue and the number busy. So for our manual simulation, we're actually going to keep track of the entities that are in queue and the entities that are in service. We have 2 events that are of interest to us. We have arrival events and we have completion events, as we discussed before. So to do this, to exercise our simulation, we just start at time 0 and we look back at our data and we say, well, the first thing that's going to happen is we're going to have an arrival happening at time 0. And so when we go to our event calendar, the first event that's going to occur is, let's just call it ARR of E1. And now once we enter this state, there are no entities in the queue. Oops, I didn't want to do that. Just going to have a blank there. And in service, we have entity E1. And so it's time 0, and the event that occurred was an arrival of E1. E1 is in service and there are no entities in queue. And so what we're interested in is, what are the next set of events going to happen? If we look back at our data, entity E2 arrives at time 4, so that happens at time 4, and entity E1 takes 5 time units, and so it begins at time 0 because it entered service, and so it finishes at time 5. And so at this point, pictorially, what we have is we have our queue here, and we have in service. Entity E1 is in service, and we have no entities in queue. And it's now time 0, and we look forward and say, when does the next event of interest happen to us? And that happens at the minimum of these 2 times. So we're going to have an arrival at time 4. We're going to have a completion at time 4. At time 5. So what we do to execute the system is we just, let's see if I can get back to my mouse here, move ahead in time. And now we just say, okay, magically it's now time 4. And the event that occurs is the arrival of E2. Since E1 is in service, then we simply place entity E2 is now in the queue. And that pictorial representation there, we can also have the numerical representation. So E2 is here, E1 is in service, and we then look forward to when the next event is going to happen. So it's time 4, and we know that we're going to have a completion at time 5. If we look back to our data, we can see that entity E3 arrives now at time 10, and so now it is time 4. We just had an arrival. So our pictorial system state is E1 is in service, E2 is in queue, and that's what we see here. And the next 2 events are going to occur. The arrival of A3 happens at time 10, The completion of E1 happens at time 5, so we simply jump ahead in time to time 5, and so this is the completion of E1. When E1, pictorially, when E1 completes, E1 leaves, and E2 moves into service. And so you see what happens is the queue now becomes empty. E2 is in service, that's E2. The next arrival still is going to happen at time 10, and we look back to our data and we see that E2 has a service time of 1, so the completion happens at time 5 plus service time of 1, so completion of E1 happens at time 6. So here we are at time 5. The queue is empty, E2 is in service, the next arrival happens at time 10, the completion happens at time 6, so we jump ahead to time 6, and so this is the completion PL of E2, and so now the queue is empty, the server is empty, the next arrival is still happening at time 10, the next completion we don't know, because we haven't had the arrival yet, so there's nothing in service. And so at this point now, the system is back to its original state of empty and idle. The server's not busy, and the queue is empty. And so continuing, the next event of interest happens here at time 10. So we jump ahead in time from time 6 to time 10, and the event is an arrival of E3. And so now the system is empty and idle, and so the queue remains empty, and entity E3 immediately starts service. We look back to our data and we see that entity E4 arrives at time 11, and entity E3 has 3 time units in service. So the next arrival will be at time 11, and the completion will be at time 10, the current time, plus the 3 time units that it takes to process entity E3, and so this happens at time 13. So it's time 10, entity E3 is in service, the queue is empty, the next arrival happens at time 11, the next completion happens at time 13, so we jump ahead to time 11, and we have the arrival of E4. So now E4 is in queue, E3 is in service, the next arrival, which would be E5, happens at time 12, and the completion of E3 happens at time 13. So then we jump ahead to time 12. Now we have arrival of E5. Arrival of E5. And so now our queue is E5 and E4. E3 is in service, and the arrival of entity E6 happens at time 16, and completion happens at time 13. So in this case, at time 12, we have entity E3 in service, we have E4 first position in queue, and we have E5 second position in queue. And continuing, it's now time 12, so we jump ahead to our next event, which is the minimum of these 2 times, so it's going to be at time 13. We have the completion of E3. So E4 jumps into service. The queue still has E5. E4 is in service. The next arrival happens at 16. E4 has a processing time of 1, so it starts at 13 and it finishes at time 14. And so now it's time 13. The entity in service is E4, and it will finish at time 14. The next arrival is at 16, so we jump ahead to time 14, which is completion of E4. So now E5 starts service, so it gets out of the queue. E5 starts service. The next arrival is at 16. Looking back at entity E5 takes 2 time units, and so that completes at time 14 plus 2, which is 16. So now we have an interesting case where entity E5 is in service. There's nothing in the queue, but two things are scheduled to happen at time 16. So the next arrival happens and the completion happens. And so these things cannot actually happen simultaneously. They have to be processed individually, but they're going to happen at the same time, as we'll see. So we'll jump ahead to 16, and we'll arbitrarily say that the next event, we're going to process the arrival first. So we're going to have the arrival of E6, and so now E6 gets in the queue, E5 is in service. If we look at the arrival time of E7, that happens at time 18. So at time 18 the next arrival happens, at time 16 the completion happens. And so now we're at time 16, and the minimum future event time is also 16. So we don't increment the clock at all. It's still time 16, and we have the completion of E5. And so now the queue will be empty. E6 will be in service. The next arrival is at time 18, and service began on E6. It takes 7 time units, so that will occur or will finish at time 23. And so you can see what happened when we had the simultaneous events at time 16. We actually processed them sequentially, but time didn't advance. And so if we look at the time that entity E6 was actually in queue, it got in the queue at time 16, it got out of the queue at time 16, so it didn't actually spend any time in the queue at all. So we would continue this process, and what I'm going to do is just sort of jump ahead through all of the events. You should definitely make sure that you can follow this. At time 16, of course, the next arrival was at 18, so we jumped to 18 for the arrival of entity 7. Then we jumped to 22 for the arrival of entity E8. Now we have 2 in the queue, and so on. And so we continue that process of finding the minimum event time moving forward. And we have 10 entities. So we only have 10 entities of data. So when this 10th entity arrived at time 28, right here at arrival 28, we had no more future arrivals. Similarly, when entity E10 finished, E10 started processing at time 30, and E10 had 6 time units required, and so it finishes at time 36. And so when it became time 36, we have no more arrivals and no more completions. And so nothing else is going to happen in our manual simulation. And so what we typically do is we stop the simulation at some point. Let's just say that we wanted to measure for the first 40 time units. So we will just have what's called the stop event. And we have nothing in queue. We have nothing in service. We have no more events. So we just arbitrarily said we are going to continue the simulation until time 40. So at this point, we started the simulation, our manual simulation. Oops, let me see if I can get a pin here at time 0, and we continued till time 40. And what we constructed is what's called a sample path. So we monitor how the system state, remember the system state is this combination of what's in the queue and what's in service, and we were looking at how the system state evolved over time as events were executed. And so again, we identified 2 events of interest, arrivals and completion, and when those events occurred at a particular point in time, they changed the system state. So when an entity arrived, in some cases we increased the queue length, as we did right here. In other cases, the server went from idle to busy, as we see here at time 10. Similarly, when entities completed, we either decreased the queue length, as we did right here, or the server went from busy to idle, as was the case here at time 6. And so we can see this evolution of the system state as events occur at discrete points in time. So in the next video, what we will look at is how to use the sample path to predict or to analyze system performance.